Greetings everybody, and today we're going to be evaluating this definite integral here, running from -1 to 1 of some linear factors raised to fractional powers divided by this quadratic. So this integral was actually suggested by one of my viewers. They sent me an email, I think it was like last month, asking for a solution to this, and yeah, I finally got around to writing down a proper solution which I'll be presenting today. So yeah, if you guys have any complex analysis or contour integral problems you want me to do on this channel, then you can send me an email. You can find my email in the about section on my channel somewhere, or you can just comment on one of my videos and I'll probably see it. But yeah, this integral, it's another one of those Dogbone contours. Would have seen it on the thumbnail, I think. And yeah, if you've watched my Dogbone contour videos, then you should probably already know how stuff is going to work out here. If not, we'll go through the details again and whatnot. I might skim over a couple of things because yeah, most of it is not too tricky to work out anyways. So yeah, how do we get started with this? Well, just like most other complex integrals, we're going to define for ourselves a new complex function. Let's call it f of z, and we're going to let f of z be equal to the integrand, but we replace all the x's with a z. So that's going to be 1 minus z minus 2 thirds and 1 plus z to the minus 1 third divided by 4 plus z squared. Now what we want to do now, we can, for example, look at the denominator and we notice there's going to be two poles. So poles, it's going to be plus and minus 2i. Because if you set the denominator equal to 0 and solve this quadratic in the complex plane, then these are the solutions you pick up. Okay, so those are the poles. We're also going to get branch cuts, which will be very important, and the branch cuts are actually going to come from these fractional powers. So how do we work with that? Well, what I'm going to do, let's define a new function, let's say g of z, and I'm just going to define it to be the numerator, so that's 1 minus z to the minus 2 thirds and 1 plus z to the minus 1 third. So I'm just taking a look at the numerator because that's where all the branch stuff cut will be happening. There's no branch cuts coming from the denominator here, only the poles which we've taken care of. So let's take a look at this. What I want to do first of all is maybe rewrite this in terms of polar form. Now how do I rewrite a function in polar form? Well, we have factors, these linear factors here. So why not write everything in terms of e to the natural log of something? So for example, this first factor, we can write it as e to the minus 2 thirds natural log, which I'll just write as log for now, of 1 minus z. And for the second factor, well, very similar, it's e to the minus 1 third, and then we have the logarithm of 1 plus z. Now what we can do, this is a log of complex numbers, so if you remember how logarithms of complex numbers work, maybe I'll remind you over here. I've made a video on this as well. If you have the logarithm of a complex number z, then this is simply equal to the logarithm of the modulus of z, so this is the real part. Then you also got the imaginary part, which is I times the argument of z. Okay, so this argument, this is something we have to choose. We have to choose the domain for this argument. That's actually why we get branch cuts when we have fractional powers, because we introduce these natural logarithms. Okay, so using this, what is our g of z? So this is going to become, so let's go down here. Well, let's write the stuff with absolute values first. So we have e to the minus 2 thirds logarithm of 1 minus z in absolute values. Let's take the second factor next, so that's e to the minus 1 third log of 1 plus z. Now let's worry about this imaginary stuff. So we also have a factor of e to here, this was 2 thirds, or with a negative 2 thirds, so minus I 2 thirds argument of whatever's in the logarithm, which is 1 minus z. And then we also have e to, this is minus a third, so minus I times a third, argument of 1 plus z. So we're basically just substituting in the definition of this log and rearranging a couple of things. Okay, now with these first two factors, we can rearrange it and collapse it back down into the absolute value of 1 minus z to the minus 2 thirds, because e and log are going to cancel. And then here, we're going to get 1 plus z to the minus a third. So this you can think about as the modulus of your function, and then we also have the argument of the function. So we can have our e over here, we can combine these two exponentials together. The i's up here will factor, so we have I, and then inside these square brackets, I'm going to put the argument of the function, which will be minus 2/3 argument of 1 minus z, and then minus 1/3 argument of 1 plus z. So this is going to be, you can say, the polar form decomposition of our function g of z. And this argument stuff over here is what's going to help us analyze the arguments and the branch cuts of our original function f of z. Okay, so now let's focus our attention to the left-hand side here. Let's draw out a little picture of what's going on. Hopefully my black marker isn't running out or anything. So what's going on with these branch cuts? So notice we have branch points at minus 1 and 1. So minus 1 and 1 over here, because that's kind of where all these arguments are centered around. So we have minus 1 and 1. Now whenever you have these fractional powers over here, these functions are actually multi-valued. Now of course a function can only have one value, so we have to make a choice of which branch we're on. And our choice of domain will actually introduce a branch cuts, and those branch cuts, since we have two of these functions with fractional powers, there's going to be a branch cut coming out of, say, minus 1 and 1. Now these branch cuts, we can orient them in really any direction we want to. So in this case, we want to ask ourselves, so what's the most useful orientation of these branch cuts that we want? Well, the most useful one would be if they're both aligned on the real axis, because we can kind of basically integrate around the branch cuts. Now there's two ways to do this. You can have both branch cuts going in the positive direction. You could have one going in the positive, negative direction, but what we're going to do is we're going to take both of them to be in the negative direction, so in the negative real axis. And the reason for doing that is because what's going to happen is these two branches, so these aren't really separate, they're actually overlapping, but just for illustration purposes I draw them like this. What's going to happen on the negative real axis below negative 1 is these two branches are going to cancel each other out. Now this is not always going to happen, it depends on what powers you have up there, but in this case it actually turns out that these branches are going to cancel out, and that leaves us with one branch cut right in the middle that runs from minus 1 up to 1. So this function f of z, in the end we're going to show this properly, but it's just going to have a little branch cut between minus 1 and 1. So if you want a picture of what the argument roughly looks like, I'm not too sure if this is the correct picture, but for those of you who've seen Riemann surfaces and stuff like that before, if you have two branch points here, but I believe you would have a picture that looks something like this. So this is kind of like the picture of the arguments. So notice I'm kind of putting this in 3D if you guys can even see what I'm trying to draw, but you have branch points at minus 1 and 1, and you're nice and continuous everywhere over here, but there's this little discontinuity between minus 1 and 1. That's actually where the branch cut is, because the value of the argument up over here is different to the value of the arguments down here. So there's kind of like a slit in this surface, if you like. And later on we're going to be doing integrals, and we're going to construct an integral up over here and an integral down over here. And it turns out, since they're on different levels, if you want, these integrals aren't going to have the same values, so they're going to differ by some constants, which we'll figure out later. But that's just some extra 3D fancy drawings if you guys are into that stuff. But yeah, let's return to what we're really dealing with here. Okay, so with this picture, there's a couple things we want to do. First of all, we want to show that we're continuous on the interval minus infinity to minus 1. And what we also want to do is we want to figure out what the argument approaches as we approach from above and below this branch cut between minus 1 and 1, because that's actually going to help us out with some integrals later on. So what I'll do now is I'll draw up a little table and we'll analyze the arguments of our function on each of these intervals. So here let's do the interval minus infinity to minus 1 but approaching from above, interval from minus infinity to minus 1 but approaching from below, and the interval from minus 1 to 1 approaching from above and similarly approaching from below. And there's no need to do the interval from 1 up to infinity because everything's going to be continuous there. Okay, and for these three columns, we're going to put the argument of 1 minus z, the argument of 1 plus z, and then finally we're going to have the argument of g, which we calculate by taking a look at this expression, but the argument of g will end up being the argument of f anyways. Okay, now before we do this, there's one important thing that I forgot to do. That's choosing the domain for the arguments. So let's put it over here. Let's take a look at the arg of 1 plus z first. Now, where does the arg of 1 plus z lie? Well, 1 plus z, that's going to be the branch that's centered around a -1, and we want it to point to the negative axis, so this is going to be on the interval, that's going to be minus pi up to pi. Now the trickier one is the arguments of 1 minus z. Now we also want this to be on the negative real axis. So you might say, well, it's the exact same thing, minus pi to pi, but it's actually not. It's because we have this reflection over here. Now in the complex plane, you shouldn't really think about negatives as reflections, rather rotations. So what we're doing here is rotating by 180 degrees or pi radians. So in fact, we want the domain of this to be 0 to 2 pi. Because this negative z, it's actually your whole entire perspective is being rotated 180 degrees. So if you want it to point in the negative direction, you should really imagine it pointing in the positive direction first, and then applying this transformation that's going to make sure the branch is pointing in the correct direction. Okay, so that's figured out. Let's take a look at the argument. Let's fill in this table. So let's take a look at the second column first, because it's a bit more easier than 1 minus z. So 1 plus z, we want to imagine ourselves centered at -1. So imagine we're standing right over here. So as we approach from above on the interval -infinity to 1, notice that looks like we're approaching, that's going to be an angle of pi. And then approaching from below, well, we're going up this way on the left, so that's going to be minus pi. And then on the interval -1 to 1, well, if we're standing over here, it doesn't really matter which way we approach, up or down, we're just going to approach 0. Okay, and for 1 minus z, well, 1 minus z, we're centered about 1, so imagine we're standing at this branch point. Now, on -infinity to -1, if we approach from above, what's going to happen? Well, remember, we have this negative over here, which makes things a little bit more tricky. So what you want to do is imagine yourself being rotated 180 degrees. So maybe flip your phone screen or computer screen 180 degrees or something and try to take a look at this. So we're trying to approach from above. So that looks something like this. We're trying to approach in that direction. So if you turn your head 180 degrees, that looks like, if we're standing at this point, that looks like we're approaching an angle of exactly 2 pi. So 2 pi is going to go over here. Then if we approach from below instead, well, imagine yourself looking at this 180 degrees over. That's, if we're standing at this point, it's going to look like we're approaching an angle of 0. Okay, and how about for these two? Well, it's very similar. If we stand at 1, if you turn your head 180 degrees, you can argue that this goes to 2 pi, and down here we go to 0. Now, a bit more of a better way to do this, if you don't like rotating your head and whatnot, you could map everything in this picture to the w plane, and w we can define as the map sending z to 1 minus z, and if you draw out the w plane now, then -1 is going to be mapped to 2, so that's going to be 2 over here, so this is w of -1, which is 2, and then 1 is going to be mapped to 0 right over here, so that's w of 1, which is 0, and this is going to become your branch cut. So you basically take this branch cut and flip it all the way over to this side, and this interval -infinity to -1 we were considering, that becomes this section over here. So yeah, in this perspective, if you take a look at approaching from, say, below, that's going to correspond to approaching from above, and you can clearly see if we were centered around 1, which in the w plane is 0, then this looks like we're approaching an angle of 0, which is exactly what we had over here. So you can do all the calculations in this perspective if you want to, or you could just rotate your head 180 degrees in the z plane. Okay, so we've basically got all the arguments down here figured out. Now we have to figure out what the argument of g would be, and thus the argument of f. So how do we calculate the argument of g? Well, we take the arg of 1 minus z, we multiply everything here by, that's 2/3, and then we take arg of 1 plus c, and then we multiply by -1/3, and then we just add the result. So let's see what we get. So over here, we're going to get a minus 4 pi divided by 3, and then minus pi on 3, but that's going to give us minus 5 pi on 3. Down over here, we're going to get 0 multiplied by minus 2/3 is 0, and then here, this is minus pi times minus 1/3. That's going to give you pi on 3. But notice, pi on 3 and 5 pi on 3 are actually congruent mod 2 pi. So really this angle is the same as pi on 3, but mod 2 pi. So in fact, on the interval minus infinity to minus 1, which is over here, the argument is actually continuous. We approach the same argument value regardless of if we come from above or below. And of course, the modulus and everything is nice and continuous on this interval. Anyways, there's no poles or anything. So yeah, the function f of z, or g of z, is actually going to be continuous across that section on that interval minus infinity to minus 1. Now if we do the same calculations over here, well, what's the argument of g going to be? This is minus 2 pi times minus 2/3 is minus 4 pi on 3, then plus 0. This is, by the way, congruent to, that would be 2 pi on 3. And then down over here, that's just going to give you 0. So notice what happens if you approach from above. You're going to approach an argument over 2 pi over 3. Whereas if you approach from below, you're going to approach an argument of 0. So the arguments, they are not congruent mod 2 pi. So the argument is discontinuous on the interval minus 1 to 1. So your function, well, there's going to be a discontinuity. So there's a branch cut there. Okay, so with that, we've basically got all the arguments figured out. This is probably the most trickiest part and technical part of this video. And everything from here will hopefully be just standard calculations. Okay, so this is basically all the information we really need. Next step is to construct the contour. Yeah, you guys should already know what the contour is. It's a Dogbone contour. So we're going to take the integral below this branch cut and also above this branch cut. And these two integrals, they're going to recover the integral I that we were after. Now we also need to construct the contour, so we need to wrap these around. So let's go around these branch points. Okay, let's label these paths. So let's call this path here gamma -1. So the path around -1. And then here, let's call this gamma 1. And let's call this path here psi 1. And then psi 2, why not? And we'll just go in the positive direction for this contour, so that's the anti-clockwise direction. And we'll call this whole entire contour here C. So let's write out some integrals and see what we have. So we have the contour integral over C, and what is that going to be? We have the integral over gamma -1 plus the integral over gamma 1 plus the integral over psi 1 plus the integral over psi 2. And basically what we want to do is take the limit as all these paths kind of tighten up. So these circles, they're going to wrap around the branch points, and these two paths, psi 1 and psi 2, they're going to become infinitesimally close. So if you remember that picture I drew, I think it was something like this. So our path psi 1 will lie right on this upper bit, and then our path psi 2, that's going to lie on this lower bit. And even though they're going to approach this interval -1 up to 1, they're going to have different values because they're on different branches. Okay, so here's the nice thing. I'm probably not going to go through this in detail in this video. I'll probably make a supplementary video, or you could check out my other Dogbone contour videos, or literally any video with branch cuts in them. The integrals around these circles are going to go to 0 because they go around your branch points. So these integrals go around the branch points, so these in the limits are going to vanish. And it's really not too tricky to check. You just need to parameterize your path integrals somehow. And then, yeah, it should be pretty clear that if you take the epsilons as they approach 0, then you have an upper bound for these and they just vanish in the end anyway. So it's really not too hard to check these. And then these two integrals, this is where our integral I will pop up. So we'll have some factors in front as well and whatnot, but we'll worry about those later. The question is now, how do we evaluate the contour integral over C? Well, this contour integral is surrounding branch cuts, so we can't really use Cauchy's residue theorem for that. Now usually what we will do is use the residue at infinity. Turns out we are not going to do that. Instead, we're going to use the fact that we have these two poles up here to actually use Cauchy's residue theorem. So how do these poles come into play? Well, remember, where are their positions? They're actually located up over here. This is 2i, and then down over here, this is minus 2i. So how do we get these two poles into the game? Well, what I'm going to do with this contour is I'm going to blow it up. And remember, contour integrals, they're path independent as long as they don't cross poles or branch cuts or anything like that. Their values will always be the same. So what I'm going to do now is I'm going to transform this contour a little bit. I'm going to imagine this is like a string or a balloon or something. Let's blow it up. So I have my poles at 2i and minus 2i down here. Now what happens if I blow this up? Well, hopefully we get a picture that looks something like this. So something that looks like this. Our contour can't cross these poles, so it's just going to do a little loop around them. So our contour is positively oriented, so this is still going to be positively oriented like so. Now here's the nice thing, everywhere I'm marked with X's or these blue lines or branch points, that's where the function fails to be holomorphic, but everywhere else our function is holomorphic, which means if you take the path integrals along these two paths, so one is going to go in, the other one's going to go out, those are going to cancel as we take the limit as they approach each other. So we can forget about that little dent in there, and just fill in this gap along with over here. And since we went in, down, and then we went, this is clockwise in here, you also have this contribution from this residue which goes clockwise. Same for down here, if we take the limit as these two paths close in, they're going to cancel each other out. So we went in, up, around, clockwise once again, so this also goes clockwise, and we can just seal in the path there. So what do we have now? We have the contour integral over here. The value of this contour integral is the exact same as all these paths down here. So let's call the big path here gamma, and then we have, let's say, gamma 2i and gamma minus 2i, and I'm also going to label these gammas with negatives to indicate they're going in the negative direction because they're going clockwise. The contour C up here, that's the exact same set of path integrals, which means all of this stuff that we've written down, this is also equal to the integral over gamma plus the integral over gamma 2i plus the integral over gamma minus 2i, and these are both going in the negative direction. So this integral over gamma, it turns out this also vanishes in the limits as we make r approaches infinity. So if we set the radius here to be r, if you take r to infinity, the integral over gamma will vanish. And yeah, that's really quite easy to show. You just have to do a parameterization or use the ML bounds or something like that. And yeah, you can see that this quadratic factor eventually kills off everything. So this integral over gamma, you guys can check that, I won't do that, but it's going to be equal to 0. So what's left is these two integrals, and these, since they're little path integrals going around singularities or these poles, then we can use Cauchy's residue theorem for that. So we have residue theorem over here, and then just some path integrals evaluate that will somehow recover our I. So that's basically the whole idea so far. Okay, so let's go ahead and evaluate these path integrals. So we have the integral over psi 1. Now how is that going to work? Well, the integral over psi 1 of f of z dz. I've done this in a previous video, but basically what we're going to do is we're going to decompose f into its polar form, very similar to kind of what we did at the very start. Now if we decompose it into polar form, we're going to have the absolute value of f of z, and then we also have times the e to the I arg of f. Now arg of f, it depends on where we're approaching it from. Now here we're approaching it kind of along the path psi 1, so I'm also going to indicate that we're going along psi 1 here. Now this is going to end up being a constant, which means we can pull it out of the integral. So this is psi 1 over here, and we can integrate with respect to z. So for psi 1, we're trying to take the limit as that path that goes from 1 to negative 1 on the top goes towards the branch cuts in blue. And what does the argument approach? It approaches 2 pi on 3. So this guy over here approaches e to the I 2 pi on 3. And notice we have the absolute value of f of z, but the thing is our function is always positive. You can check this by yourself. It's not too tricky to see, or you can just look at the graph which I showed you at the start of this video. This function is positive everywhere, so the absolute value really doesn't change anything. Now this path psi1, in the limit, what does it approach? It approaches the interval 1 to -1. So we're going to go from 1 back to -1. But this over here, notice that it's simply I, but in the negative direction, in the other direction, because I, we're going from -1 to 1. Here we're going from 1 to -1. So in the end, this is minus e to the I 2 pi and 3 times I, but negative, that's just an extra 180-degree rotation, so I can rewrite this e to the I 2 pi and 3 as e to the minus I pi on 3, and then times I. So that's what the integral over psi1 evaluates to, and we can do a very similar thing for the integral over psi2 of f of z dz. We're going to have e to the I argument of f on side 2, and then we have the integral. Now we're going from -1 to 1 on side 2, we're going to the right, so this is -1 to 1 absolute value of f of z dz, and then by the same reasoning from before, you can see that this evaluates to I, and this will arg over f, that's going to approach 0 if we go from below, so this overall just approaches 1, so this integral is just simply I. So that's quite nice. So you know what the integral over psi1 and psi2 are going to evaluate to. Okay, so now let's figure out these two integrals, which is those residues from before, which are these two path integrals down here. So let's take a look at the integral over gamma 2i with a negative of f of z dz. Well, by Cauchy's residue theorem, this is going to be 2 pi I times the residue at z is equal to 2i of our function f of z. But notice one important thing. This contour is negatively oriented, which means we also have to include a negative to compensate for that. Now you can clearly see 2i, that's going to be a simple pole, because this quadratic factors into linear factors, so this is going to give us minus 2 pi I. Using the definition for residues at simple poles, this is the limit as z approaches 2i of z minus the pole, which is 2i, times the function, which is, well, that g of z we had before, which I'll just write for the numerator because I'm too lazy to write out the whole thing, divided by this quadratic factors into z minus 2i and z plus 2i, and these factors here are going to cancel. So what is this going to give us? This is going to give us minus 2 pi I, and then there's no problems with the zeros or anything here, so it's safe just to sub in 2i. We have g of 2i divided by 4i. And we can do some cancellations here. We still have a negative. 4i and 2i, that's going to cancel out to a half. Then we have pi on 2. Then what's a g of 2i? Well, that's just the numerator, but evaluated at 2i. So we're going to get 1 minus 2i to the power of minus 2/3, then 1 plus 2i raised to the power of minus 1/3. So over here, what can we do? Well, we have a complex number raised to a power. Let's use the complex logarithm. And essentially we're writing all this stuff in polar form, but we've basically already done it at the start of the video. So we can just do a little bit of a shortcut. You can just take the absolute value. So this is 1 minus 2i, then minus 2/3. And then multiply it by the argument. So this is the modulus. Then we have e to the I argument of 1 minus 2i. And I've got a negative 2/3 there. And then same deal over here. This is going to be 1 plus 2i raised to the minus 1/3, e to the minus 1/3 I, and then arg of 1 plus 2i. Now here's where we have to be careful, because remember with this argument function, the one which is associated to the power of minus 2/3, what's the domain of this? This is on the interval, well, it was 0 to 2 pi. And then this argument function here, which is associated to the power of minus 1/3, we define that to be on the interval minus pi to pi. So this is something we have to be quite careful about, because if we do it the wrong way, which is actually what I did when I first solved this, then you're going to have problems with things being imaginary, which you don't want them to be. For example, if you do the calculation over here quite naively, then what you get on the right hand side on this equation is a real number, but clearly the left hand side here is complex. So you have this kind of mismatch between real and complex. So it's important to pay attention to this stuff. So let's take a look at this. So what's going to be the argument of 1 minus 2i? Well, let's draw up a complex plane picture over here. 1 minus 2i looks something like this. So this is 1 minus 2i. Let's draw up 1 plus 2i as well. Why not? Now notice both of these have these angles in here that are the same. Let's call it phi. So what could phi be? Well, it's simply the arctangent of 2, because if you do opposite over adjacent, that's 2 over 1 for both of them. So here we can define phi to be equal to the inverse tangent of 2. So the argument of 1 minus 2i, if you are doing this a little bit naively, you would say, well, that's just minus phi. But it's actually not, because remember, our argument is on the interval 0 to 2 pi. So you need to add an extra 2 pi. You need to go 2 pi, then subtract off phi. So this is actually minus I to the 2/3, and then times 2 pi minus phi. And in fact, when I first did this is where I went wrong. I left out this 2 pi and then I had some problems. So you need this to make everything work out nicely. And then over here, you have the absolute value of 1 plus 2i. Let's actually replace that with what it actually is. I think it's like root 5 or something. So if you do 1 squared plus 2 squared, that's 5, I think. So root 5. And then over here, we also have root 5, but raised to the minus 1/3. So, and then here we have e to the minus I 1/3. And then for this argument, this is 1 plus 2i, the argument is phi, and that's clearly on the interval minus pi to pi. So we're safe just to write down phi there. Okay, let's clean things up a little bit over here. So here we have root 5 raised to the minus 2/3 times root 5 raised to the minus 1/3. Overall, there's going to be root 5 raised to the minus 1, which is just 1 over root 5. Then we have e2, let's distribute over here. So we're going to get minus 4 pi over 3 times I, and then we have e, and then we also have these double negatives here are going to cancel, so that leaves us with e to the I 2 pi on 3 times phi, but we also have this negative I 1/3 phi, so if you add the two angles together, you're actually going to get e to the I 1/3 phi, like so. And finally, I guess the last little simplification we could do, and we can rewrite minus 4 pi and 3 as this 2 pi and 3, because those are really the same angle. Okay, cool. So this over here, that's the value of this. That's the little contour circle thing around here at 2i. So on this integral, we know it's a value. It's going to be minus pi, Okay, so now let's erase most of this stuff and we'll repeat the same thing for minus 2i. Nothing much is going to change. So for these first couple steps, everything's basically the same. We still have this negative because we're going in the negative direction. And then up to here, this is still a negative here. But now instead of cancelling z minus 2i, we're cancelling z plus 2i. And then this plus here, that will be a negative. And yeah, let's erase out everything over here because things are going to start looking slightly differently. So here we're going to get minus 2 pi I, and if we plug negative 2i in again, there's no problems with things blowing up or whatnot. So this is g of minus 2i divided by, this is going to give us a minus 4i down here. These negatives are going to cancel. This 4 and 2 will cancel to give us a half, and these i's will cancel as well. So overall, this is a pi divided by 2. Then we plug a minus 2i into our g. So what is that going to look like? It's going to look like 1 plus 2i raised to the minus 2/3. Then 1 minus 2i raised to the minus 1/3. And again, we can do the little polar form decomposition. So this is pi on 2. Absolute value of 1 plus 2i raised to the minus 2/3. We can write the magnitude of this second factor next. So that's going to be 1 minus 2i raised to the minus 1/3. Now we can do the arguments. So that's e. This is a minus 2/3. So minus I 2/3. Argument of 1 plus 2i, then e to the, this is a minus 1/3, so minus I over 1/3, then arguments of 1 minus 2i. So remember this guy over here, this argument that was on the interval 0 to 2 pi, whereas this argument over here, that was on the interval minus pi to pi. So let's do the calculations now. So just like before, all of this stuff over here with the absolute values, that just becomes 1 over root 5. So this is 2 divided by root 5. Then let's see what we have over here. Well, 1 plus 2i, the argument of that, that's going to be phi. That's definitely on the interval 0 to 2 pi. So we can just write e to the minus I 2 over 3 phi. Then over here, we're going to have e to the minus I 1/3. Arguments of 1 minus 2i, that's minus phi, but nicely that's on the interval minus pi to pi. So we can just plug in minus phi here without having to add any angles. So overall, what is this going to give us? We have pi divided by 2 square root of 5. Then these negatives, they're going to cancel. Then we're going to get negative 2/3 plus 1/3. So overall, that's going to be, I believe that should be negative 1/3. So we have minus I 1/3 times phi, and that should be the value of this little contour integral. We should really have put circles here, but really doesn't quite matter. So overall, what's the value of the integral over here? That's going to become pi over 2 square root of 5 e to the minus I pi over 3 times 5. Okay, so those are basically the important calculations done. So we have these two added together is equal to what we have on the left hand side here. So now let's clean up the board and we'll try to figure out the final value for our integral I. So the first thing I'm going to do, I want to simplify the left hand side a little bit so we can factor out an I, and what we'll be left with is e to the minus I pi on 3 and then plus 1. But notice we can actually simplify this, because if you take a look at the complex plane, let's draw it down here, e to the minus I pi on 3, that's, you can think about as a vector pointing down with an angle of pi on 3 in here. And then we're adding 1, which is just a vector pointing sideways with the same magnitude. Now if you add these together, you're going to get a vector pointing in this direction, and yeah, you can argue that this angle, that should have been 2 pi on 3, which means that these two angles on the sides of this isosceles triangle, they're going to be pi on 6. So the angle in here, that's going to be pi on 6. So what's the length of this arrow going to be? Well, we can use cosine rule for this. We know the length of these arrows over here, these vectors, they're 1. So we have something like c squared equals a squared plus b squared minus 2ab cosine c. So we have 1 squared plus 1 squared, which is 2, minus 2, ab and 1. Then we have cosine of c, but c is going to be 2 pi on 3. Cosine of 2 pi on 3, that's minus a half. So this overall, well, this part over here, that's going to be a 1. So we get 2 plus 1, which is 3. So c is going to be square root of 3, which is the size of this arrow. So this complex number in here, we can write it as, well, square root of 3 times e to the minus I pi over 6. Now, as for the right hand side, we have all this mess going on. We can simplify it a little bit. So what I'm going to do, we have some factors here that look the same, so we can factor that out. So this is equal to, let's factor out minus pi divided by 2 square root of 5. Now what I'm also going to do is factor out e to the I pi on 3. Even though we have a 2 pi on 3, I'm just going to factor out pi on 3 because I also want somewhat of a similar factor on the second term to turn it into a sine function. So we're going to have e to the I pi over 3 factored out. Now what are we going to be left with on the inside? We're going to be left with, well, there's still an e I pi on 3 that's still in there. Then we have e to the I 1/3 phi. Now we factored out a negative here, which means that this plus is going to flip to a negative. This pi over 2 root 5 is factored out. Then we have e to the minus I 1/3 phi, but remember we also factored out e to the I pi on 3. There was no e to the I pi on 3 here, so we're going to get an extra factor of e to the minus I pi on 3. And hopefully you guys see where this is going. I think I mentioned it before. We're going to turn this into a sine function. I'm not quite ready for that yet because we're missing a 2i down here. Luckily we can steal the number 2 over here and just place it in over here. And we're also missing an I, so let's put down an I and put down an I somewhere else in the numerator. Let's say over here. Okay, so all of this stuff, that's going to become minus pi over square root of 5, I e to the I pi on 3. So this is kind of like E-I-E-I-O, but there's no O, there's a pi on 3. And now all of this stuff, it's going to become, let's write it out as E. We can factor out I, then we have pi on 3. Plus, let's just write it as phi on 3. That rhymes, pi on 3 plus phi on 3. Then we have minus E, let's factor out minus I. Then we also have pi on 3 plus phi on 3. Then this is divided by 2i, and this is exactly the sine function. We have e to the I something minus e to the minus I, the same something over 2i. So this is overall minus pi over square root of 5 I e to the I pi on 3. Then we have the sine function of pi on 3 plus phi on 3. And in fact, we're very quite close. The very final thing to do is isolate this I by dividing both sides by square root of 3 e to the minus I pi on 6. So let's go ahead and do that and see what we get. So I in the end is going to be equal to, if we divide both sides by root 3, we're going to get a root 3 down here. We can combine it with this root 5 to give us root 15. So here's our root 15. Then we have to multiply both sides by e to the I pi on 6 to cancel with this factor. Now if we do that, what are we going to get? Well, we're still going to get the I here. We're going to have e to the I pi on 3 plus pi on 6. But pi on 3 plus pi on 6, that's exactly pi on 2. So this is e to the I pi over 2. Then we have the sine of pi on 3 plus phi on 3. Okay, but e to the I pi on 2, that's simply I, and I times I, that's exactly negative 1. So in fact, this negative out here and this whole entire thing, which is negative 1, will cancel, and this leaves us with the final answer of our integral I being equal to pi divided by the square root of 15 multiplied by the sine of pi on 3 plus phi on 3, but remember what was phi? It was simply inverse tangent of 2, and then we have a divided by 3, and this is the final answer to our integral. So I'm not too sure if there's a simpler closed form for this, or if you can simplify it further. I plugged it into a calculator thingo. I think it's like Symbolab or something, but yeah, this was the simplest answer it could give me. So I'll go for this as the answer. I think it's approximately like 0.801, I think. So yeah, interesting answer. Just looking at this, you wouldn't really expect a 15 to pop up, but 15 does pop up somehow, which is cool. And yeah, we have an inverse tangent inside of a sine, which is really quite interesting. So yeah, that's the final result for today's integral, and yeah, that's basically the whole video done. So hope you guys enjoyed this video. As I said at the very start, if you guys have complex analysis problems you want me to do, any contour integral things, let me know, because I am kind of running out of ideas. I have a couple more ideas on complex analysis things I want to do, but after that, it's really what you guys want to put on this channel, and I'll do it, because yeah, there's some very niche stuff that I can put on as well, but not sure if people will end up watching that. But yeah, anyways, up until the next one, have yourselves a wonderful day, and I'll see everyone later. Bye bye.